So now that we've got this idea of complex numbers, the imaginary number, let's look at solving quadratics in a bit more detail. Now, I said to you earlier that it actually wasn't quadratics that created the imaginary number. It actually was the problem of trying to solve a cubic. So let's just look at this very simple quadratic. X squared plus 3x plus 7 equals 0. So we could, of course, just go to our quadratic formula. But now that we have the square root of 19, we can simplify the third. Because we know square root of negative 1 is I, and so there's our answer, negative 3 plus or minus root 19i on 2. And if we want to split it up into two solutions, there they are. Of course, you could do it that way. Of course, another way you could do it is completing the square. You can now complete the square on any quadratic, because you can write anything now as the difference of two squares. Okay? So x squared plus 3x plus 7, which would be x plus 3 on 2 all squared plus 19 on 4, which you're looking at and thinking, hang on, that's the sum of two squares. But I can make it the difference of two squares by changing it to minus 19 on 4 I squared. And it's now the difference of two squares. So therefore, it's x plus 3 on 2 plus root 19 on 2i, x plus 3 on 2 minus root 19 on 2i. There's our two solutions. So it does now give us another way of solving quadratics. Everything can be done via difference of two squares. All right. All quadratics, not only quadratics, for that matter, any polynomial, seeing we've recently been talking about polynomials, if all the coefficients of the equation are real, then any imaginary solutions must appear in conjugate pairs. It must appear in conjugate pairs. So what that's saying is then, we know a quadratic could always be factorised as x minus z conjugate. If I was to expand that out, on the right hand side you'll see I get x squared minus z plus z conjugate x and z times z conjugate, which gives me x squared minus 2 times the real part. So if you add a number with its conjugate, the imaginary parts are going to disappear, they'll cancel out. So you'll get twice whatever the real number is. And z times z conjugate, well, we saw before, that ends up being the sum of two squares. So this idea then, we saw it before when we looked at quadratics, but now we can do it with imaginary solutions as well. The quadratic equation, which has roots 4 plus I and 4 minus I, it still is really, whilst I did it in a very fancy way up there by going z plus z conjugate, it still is sum of the roots, product of the roots. So the sum of the roots is going to be 8. The product of the roots, sum of two squares, will be 17. So therefore my quadratic is x squared minus the sum of the roots x plus the product of the roots, and there it is. So we can create quadratic equations if we know the solution. More interestingly, finding the square root of numbers. But let's find the square root of not real numbers, but complex numbers. Things that have an imaginary part. So we're going to say the answer is a plus ib. The square root of x plus iy, answer a plus ib. What is it? Well, to work out a formula to do this, I could square both sides. Now on the left hand side I've got a perfect square. So I'll get a squared plus twice the product. But remember, I've got the I squared, so it becomes minus b squared, not plus b squared. And then equate the real part and the imaginary part. So if the square root of x plus iy, the answer I'm looking for is a plus ib, then the difference of two squares, in this case it is the difference, a squared minus b squared will be the real part, 2ab will be the imaginary part. So let's find the square root of minus 12 plus 16i. So a squared minus b squared, the real part, negative 12. 2ab, the imaginary part. Once again, we've got simultaneous equations. So b ends up being 8 on a. Sub it into the other one. We end up with a quartic, which we can treat as a quadratic. Multiplies together, negative 64, adds together, give 12. We have negative 4 and plus 16. So either a squared equals 4 or a squared equals negative 16. But remember, a and b, real part, imaginary part, they're both real numbers. Therefore, a squared equals minus 16 is not a solution. So it must come from the a being plus or minus 2. If I sub back in to get the b, it's going to be 8 over 2, which is 4. As I say, the negative 16 doesn't give me any solutions. There's my answer. And this is going to bring up probably the first controversial thing. You see, if I had said to you, what is the square root of, let's pick a number, 25? You would give me the answer, right. You wouldn't say plus or minus 5. But when I'm dealing with complex numbers, remember, you can't order complex numbers. So the square root of negative 12 plus 6i, is it plus 2 plus 4i, or is it minus 2 minus 4i? Again, you can't order them. Now, some books will say that you always take the real part to be positive. So when you're looking at some solutions, they'll go like that. I always put both down because I disagree with that. I said, well, you can't say which one's the positive square root, which one's the negative square root, because it has no meaning when we're not talking about a number line. So I always put both down. Let's have a look at another idea. A plus ib, remember, it's square root of x plus iy. We just saw that a squared minus b squared was equal to x and 2ab was equal to y. If I play around with this a little bit, don't worry, you don't have to do this every time, you just have to remember what we're going to end up using. But playing around with it, remember that x squared plus y squared? Significance of that number times its conjugate, right? I could create that. So x squared plus y squared, if I sub in the a squared minus b squared and the 2ab, ends up being a to the power of 4 plus 2a squared b squared plus b to the power of 4. So what that means is a squared minus b squared is equal to x. We know that. A squared minus b squared will be the real part. But a squared plus b squared will be the square root of the sum of two squares. Because if you look at the a4, if I was to factorise that, I would get a squared plus b squared squared. So therefore, a squared plus b squared is the square root of x squared plus y squared. Now, how do you know whether they have the same sign or the different sign? Well, it's all to do with the imaginary part. If the imaginary part is positive, then your solution a and b will end up with the same sign. If the imaginary part is negative, then a and b will end up with different signs. So all to do with the imaginary part. So our same question, rather than doing all those simultaneous equations, I can say, well, a squared minus b squared is negative 12, the real part. A squared plus b squared is the square root of the sum of two squares. 144 plus 256, 16 squared. Add them together, you get 400. Square root of 400 is 20. A squared plus b. Much easier simultaneous equations to play with. Because now I can say, 2a squared is 8. A is 2. I don't have to worry about plus or minus because I'm going to end up having plus or minus anyway. So a is 2. Sub back in, b is 4. The imaginary part is positive. Therefore, the solution has the same sign. So it's plus or minus 2 plus 4i. Okay? It's a neat little way of doing it. All right, let's find the square root of 5 minus 4i. Let's do it that way. Oh, well, here we get into a little bit of a problem using that second method. Because now a squared plus b squared ends up being the square root of 41. Hey, it still works. Just bear with me. Solve them simultaneously. A ends up being a half of the square root of 10 plus 2 root 41. Hey, it's a number. It's a solution, okay? It might not look pretty, but it is a number. Yes, you can sub back in. And you get b. B ends up being a half square root of negative 10 plus 2 root 41. So therefore, there's my answer. Why? Piece of cake. All right, what was different between the two questions? Why did this one turn out to be so messy and the other one turned out so neat? There's a really significant difference between the two questions. Have a look at the numbers. Okay, so you've got 5 and 4, and this one you've got 12 and 16. Yeah, Pythagorean triads. Right, so there are two smaller numbers of a Pythagorean triad. That method will work beautifully for something that gives you start with two numbers of a Pythagorean triad. If it's not, and 4 and 5 are not, then you'll end up with something messy. Now, look, there's nothing wrong with that answer. It is a correct answer. Okay, but a bit of playing around with it. All right, let's solve this quadratic. And you might look at this the first time you see something like this and go, oh no, well what? Imaginary numbers, it's just a quadratic equation. Then it's numbers, 2 plus I. No difference, the maths doesn't change. Use the quadratic formula. So minus 2 plus I, negative b plus or minus square root of b squared minus 4ac. Oh good, 5 and 12, yes. 5 and 12 are two smaller numbers of a Pythagorean triad. So I can work out that square root. I'll just do that to the side. That one will work out nicely. We get a is 2, b is 3. The imaginary part is positive, so they'll have the same sign. So we get plus or minus 2 plus 3i. And, well, let's play around with that and we get our two answers. Now when you look at these two answers, you sort of kick yourself. Because think about it logically. What multiplies together to give the last number? What adds together to give the middle number? Oh, of course, minus 2i, and I. They would multiply together to give 2 minus 2i. They would add together to give 2 plus I. You might not see that straight away. But it's, oh damn, why didn't I spot that just sort of thing? Alright, so I'll just add those questions in. So from our Cambridge.